Welcome to this deep dive into function decomposition, a powerful method for systematic invention and innovation. Function decomposition breaks complex systems into fundamental functions, opening pathways to alternative solutions and breakthrough innovations. Let us begin by understanding what function decomposition means and why it matters for invention. A function describes what a system does, not the specific physical mechanism used to accomplish it. Think of it as separating verbs from nouns in engineering. The function is the verb, the physical mechanism is the noun. For example, the function might be to transport mass, but we could achieve this with a pump, a conveyor belt, pneumatic pressure, or gravity flow. Most engineering systems rely on a small set of fundamental functions that appear again and again. First, to transport mass or energy from one location to another. Second, to convert one form of motion or energy into another form. Third, to separate components of a mixture or combine separate streams. Fourth, to store mass or energy temporarily and release it when needed. These four core functions form the building blocks of almost every engineered system you encounter. Let us examine the transport function in detail, starting with moving mass through systems. Bernoulli equation governs fluid transport, relating pressure, velocity, and height at different points in a flow system. Consider a practical example. We need to transport 100 liters per minute of water up 10 meters. The volumetric flow rate is 100 liters per minute, or 1.67 times 10 to the minus 3 cubic meters per second. The minimum power needed is density times gravity times height times flow rate, giving approximately 167 watts. Now, what are the alternative physical effects we could use to accomplish this transport function? We could use centrifugal pumps, positive displacement pumps, pneumatic pressure, gravity siphons, or even magnetic coupling for special fluids. The convert function transforms one type of motion or energy into another form. Newton's second law, force equals mass times acceleration, governs mechanical conversion of forces and motion. Consider converting rotational motion into linear motion, a common requirement in many machines. A rotating input on the left produces linear motion output on the right. Many physical mechanisms can accomplish this conversion. We could use rack and pinion, lead screws, belt and pulley systems, or cam and follower mechanisms. For a simple case, linear velocity equals angular velocity times radius. If we have 1000 RPM rotation with a 5 centimeter radius wheel, what linear speed do we get? 1000 RPM converts to approximately 105 radians per second. Multiplying by the radius gives 5.25 meters per second linear velocity. But we could achieve the same functional conversion using hydraulic cylinders, pneumatic actuators, or even piezoelectric elements. The separate function divides mixed components based on physical or chemical differences. Fick's law of diffusion describes how concentration gradients drive separation, with flux proportional to the concentration gradient. Consider the practical problem of separating oil from water, common in many industrial processes. Oil droplets, shown in yellow, rise to the top due to density difference, while water, shown in brown, stays at the bottom. We can exploit many physical properties for separation: density differences, particle size, electrical charge, solubility, or magnetic properties. The density difference between water and oil is roughly 100 kilograms per cubic meter. Stokes' law gives the settling velocity based on droplet radius, density difference, and fluid viscosity. For 100 micron droplets, settling velocity is about 0.1 millimeters per second, requiring hours for gravity separation. To speed this up, we could use a centrifuge providing 10,000 times gravity, membrane filtration, or coalescence techniques. Here is the key innovation question that drives breakthrough thinking. What if we keep the desired function exactly the same, but change the underlying physical mechanism completely? One function can map to many different physical implementations, each with unique advantages and limitations. This simple question unlocks innovation by vastly expanding the space of possible solutions we consider. Let us explore a detailed case study of mixing fluids to see function decomposition in action. The function is clear. Achieve a homogeneous mixture of two initially separated fluids. Reynolds number characterizes flow regime, relating inertial forces to viscous forces in the fluid. The traditional solution uses a mechanical impeller, rotating in the fluid to create turbulent mixing. An impeller shaft drives blades that create swirling flow patterns throughout the container. Power consumption scales with the cube of rotation speed and fifth power of impeller diameter. For a 10 centimeter impeller at 100 RPM in water, we need roughly half a watt of power. But what if we change the physics completely while keeping the mixing function? Static mixers use fixed geometric elements to split and recombine flow streams, requiring no moving parts or external power. Ultrasonic mixing uses high-frequency sound waves to create cavitation bubbles that violently mix the fluids. Magnetic stirring uses a rotating external magnet to drive a magnetic follower inside a sealed container. Jet mixing injects one fluid at high velocity into another, using momentum transfer for mixing. A static mixer uses twisted vanes that split and recombine the flow repeatedly, achieving excellent mixing with only pressure drop as the energy cost. Let us examine temperature control as another rich example of function decomposition. The function is to maintain a system temperature within plus or minus 1 degree Celsius of a set point. Heat capacity relates heat flow to temperature change through mass and specific heat capacity. Consider heating 1 liter of water from ambient 25 degrees to target 80 degrees Celsius. The energy required is 1 kilogram times specific heat of 4,200 joules per kilogram Kelvin, times temperature change of 55 degrees giving 231 kilojoules. If we want to heat this in 5 minutes or 300 seconds, we need 770 watts of power. The traditional approach uses an electrical resistive heating element immersed in the water. But many alternative physical mechanisms can deliver this heating function. We could use resistive heating, induction heating, microwave absorption, or a heat pump to transfer energy from the environment. A heat pump can deliver 3 to 4 joules of thermal energy for every joule of electrical energy consumed by moving heat rather than generating it. Coefficient of performance for a heat pump is typically around 3.5 for this temperature range. By changing the physical mechanism from resistive heating to heat pump, we achieve the same function with 3 times better efficiency. Function decomposition applies equally well to electronic and information processing systems. Consider the function of storing and retrieving 1 gigabyte of data with fast access times. Traditional solutions use semiconductor flash memory with electrical charge storage in floating gates. Flash memory stores data as electrical charges in a grid of transistor cells with electronic readout. What alternative physical mechanisms could store and retrieve this information? Magnetic storage uses magnetic domains in ferromagnetic materials, as in hard disks or magnetic tape. Optical storage uses reflective pits or phase changes readable by laser, including holographic volume storage. Mechanical storage like punch cards was used historically with physical holes encoding information. Chemical storage includes DNA molecules for ultra-dense archival storage or photographic film emulsions. DNA storage achieves densities of 10 to the 19th bits per cc, far exceeding any electronic technology. Let us now formalize the complete invention process using function decomposition. Step 1. Identify the core function you need, stripping away all assumptions about how it is currently implemented. Step 2. Express the function abstractly using action verbs like transport, convert, separate, store, or sense. Step 3. Systematically list all known physical effects that could potentially realize this function. Step 4. Make back-of-the-envelope estimates of key parameters like power, size, cost, and speed for each physical effect. Step 5. Evaluate the trade-offs and select the most appropriate implementation for your specific constraints. The process flows from identifying a need, abstracting to function, then expanding to multiple physical implementations. Real systems combine multiple functions, creating rich possibilities for innovation. A complex system is essentially a sequence or network of basic functions connected together. Functions chain together in sequence, with the output of one becoming the input to the next. The power of this approach is that each function can be replaced with alternative physics independently of the others. If each function has multiple physical implementations, the total design space grows multiplicatively. With just 3 functions and 4 options for each, we already have 64 possible system designs to consider. Let us decompose an everyday device, a coffee maker, to see these principles in action. What are the essential functions required to brew coffee? Function 1. Heat water from room temperature to 90 to 95 degrees Celsius. Function 2. Transport the hot water to the coffee grounds. Function 3. Mix water with grounds to extract the soluble coffee compounds. Function 4. Separate the liquid coffee from solid grounds. These 4 core functions can each be implemented using different physical mechanisms. Heating could use electrical resistance, induction, direct flame, or even solar concentration. Transport could rely on gravity drip, pressure from boiling, vacuum suction, or a mechanical pump. Separation might use paper filters, metal mesh screens, cloth, or even centrifugal force. Different combinations of these mechanisms yield drip coffee makers, espresso machines, French press, percolators, and more. Function decomposition helps identify where energy is consumed and how to improve efficiency. Each function has a theoretical minimum energy based on thermodynamics and fundamental physics. For chemical or phase changes, the minimum energy is the Gibbs free energy change. The actual energy required equals the minimum divided by the efficiency of the physical mechanism chosen. This simple relation shows how efficiency multiplies energy requirements. Consider the efficiency of different water pumping mechanisms. The minimum energy to lift 10 kilograms of water up 10 meters is exactly 1,000 joules. A typical centrifugal pump at 60% efficiency needs 1670 joules. A positive displacement pump at 85% efficiency needs only 1180 joules. Choosing the right physical mechanism directly impacts energy consumption, operating cost, and environmental footprint. The verb and noun analogy provides an intuitive way to think about function decomposition. The function is like a verb in a sentence, describing what action the system performs. The physical effect is like a noun, specifying the specific mechanism used to perform that action. To transport mass is the verb. Using a centrifugal pump is the noun that specifies the mechanism. Invention is like rewriting sentences, keeping some parts while substituting different verbs or nouns to express the same idea differently. Using different physical mechanisms for the same function is analogous to choosing synonyms that convey the same meaning. When should you consider changing the physical mechanism rather than optimizing the existing one? First signal, when your current approach is approaching fundamental physical limits and further optimization yields diminishing returns. Second signal, when new constraints emerge, such as size limits, temperature ranges, or material restrictions. Third signal, when you need radically different performance, say 10 times faster or 1/10 the energy. Fourth signal, when new physical effects or materials become available that were not options before.